Hello, I'm Engineer Gladys Grace de Restauro and I will be discussing about semiconductor diodes. Okay, there are three materials that are used in making a semiconductor. The germanium, Ge, silicon, Si, and gallium arsenide, or GaAs. Semiconductors are those materials whose conductivities exist between conductors and insulators. They have poor conductivity than conductors and higher than insulators. When the temperature of a semiconductor is increased, its resistivity decreases or conductivity increases. Therefore, the semiconductor has negative temperature coefficient of resistance. Okay, so covalent bonding and intrinsic bonding. The fundamental components of an atom are the electron, proton, and neutron. In the lattice structure, neutrons and protons form the nucleus and electrons appear in fixed orbits around the nucleus. So if we look here in the figure, this is the lattice of a silicon and a germanium. A silicon has 4 valence electrons, as you can see in the figure. And the germanium in figure B, there are 4 valence electrons also. Okay. In gallium, there are 3 valence electrons. In arsenic, there are 5. So this bonding of atoms strengthened by the sharing of electrons is called covalent bonding. Okay, if you look in figure 1.4, covalent bonding of the silicon atom, this is what it looks like when they share electrons. So that is the covalent bonding of silicon atom. And covalent bonding of the gallium arsenide looks like this in figure 1.5. This bonding of atoms strengthened by the sharing of electrons also. So this is the covalent bonding of the gallium arsenide. Covalent bonding and intrinsic materials. The term intrinsic is applied to any semiconductor material that has been carefully refined to reduce the number of impurities to a very low level, essentially as pure as can be made available through modern technology. So that's what we call intrinsic. For conductors, the resistance increases with an increase in heat. Okay, I already tell that earlier that with the increase of temperature in the semiconductor, its resistivity decreases or conductivity increases. Therefore, semiconductor materials have a negative temperature coefficient. Okay, it is significant, let's go back here, it is significant that the conductivity of these materials, the semiconductors, can be varied over orders of magnitude by changes in temperature, optical excitation, and impurity content. So that is the semiconductors. In the energy level, the farther an electron is from the nucleus, the higher is the energy state. And any electron that has left its parent atom has a higher energy state than any electron in the atomic structure. Okay, let's look here in the figure. If the nucleus is below, look at the lowest blue line. If the nucleus is there and the valence level is at the top blue line, so the farther the valence level, the higher the energy it creates. So if we look here, the difference with the insulator, semiconductor, and the conductor. Okay, in the insulator, the conduction band is longer than the semiconductor, and the conduction band in the conductor is lower. So the energy level of a germanium, based here in a figure, 0.67 electron volt. EV is, that means electron volt. And in the silicon, 1.1 electron volt, and the gallium arsenide, 1.43 electron volt. Okay, an electron in the valence band of silicon must absorb more energy than one in the valence band of germanium to become a free carrier. Similarly, an electron in the valence band of gallium arsenide must gain more energy than one in silicon or germanium to enter the conduction band. So if you look at the equation for the electron volt, energy equal to charge times voltage. 1.6 times 10 to the power of negative 19 coulombs times 1 volt equals to 1.6 times 10 to the power of negative 19 joules. So that is the equivalent of 1 electron volt. 1 electron volt equals to 1.6 times 10 to the power of negative 19 joules. Okay, there are N-type and P-type materials that are used in making a semiconductor. A semiconductor material that has been subjected to the doping process is called an extrinsic material. Diffused impurities with 5 valence electrons are called donor atoms. Diffused impurities with 3 valence electrons are called acceptor atoms. So let's go back here. The donor atoms are what we call N-type, and the P atoms are what we call a P-type rather is called the acceptor atoms. So those that have donor atoms are what we call N-types, and the acceptor atoms, those that have acceptor atoms, that is the P-types. Okay, semiconductor diode. This is the symbol for a diode. The simplest semiconductor device. It is a two-terminal device. So let's look at figure A. So there is a polarity, positive to negative. So current ID, and then the voltage of that diode, the simplest semiconductor device. So voltage V sub D. Okay, always remember the symbol for a diode. Ideally, it conducts current in only one direction and acts like an open in the opposite direction. So if you look here, the polarity and the first diode, positive to negative. So the current flows from positive to negative. So ideally, it will become short circuit when the current flows to the diode. So where voltage is V sub D, voltage V sub D is 0. And when you look at the diode below that, the polarity negative to positive. So the current flows from negative to positive. It creates an open circuit, meaning the current is 0. The current I sub D equals 0, and the voltage is negative. Okay, we look at the graph. So the color green, the I sub D for the short circuit approaches infinity, and then voltage V sub D in the open circuit is a negative infinity. Okay, characteristics of an ideal diode. Okay, look at the vertical line. Positive, that is a positive current, positive I sub D. and that is the current for an ideal diode that uh, an ideal diode with the current that flows from positive to negative polarity. Okay, in the conduction region, ideally the voltage across the diode is 0 volts and the current is infinity. The forward resistance, or that is R sub F, forward resistance, is defined as R sub F equals to voltage of the forward resistance divided by a current of the forward resistance. So that is RF equals to V sub F divided by I sub F. The diode acts like a short. Okay, so that is for the ideal diode. And when we look at the non-conduction region, in the non-conduction region, ideally, all of the voltage is across the diode. The current is 0 ampere, and the reverse resistance, that is R sub R, is defined as R sub R, or that is the reverse resistance, equals to voltage of the reverse resistance divided by the current of the reverse resistance. And the diode acts like open. So you'll see here in the figure. Okay, for the common material used in the development of semiconductor devices, so pinaka-common, silicon and the germanium. Okay. If we look at their characteristics, higher current, voltage rather, so up equivalent to 1000 volts. And then for the germanium, 400 volts. For the silicon, it has a higher current rating, and for the germanium, lower current rating. And for the silicon, it has a wider temperature range that is up to 200 degrees Celsius. And the germanium, a narrow temperature range lower than 100 degrees Celsius. And the higher forward bias voltage of the silicon is 0.7 volts, while the germanium has a lower forward bias voltage, or 0.3 volts. Okay. So PIV means peak inverse voltage. So that are the differences of a germanium and a silicon diode. If we look at the graph, comparison of silicon and germanium silicon diodes. So these are the graphs of their currents versus voltage. So the saturation of silicon, the red line, is 0.7 volts. And the saturation of germanium is 0.3 volts. A semiconductor diode with applications too numerous to mention is created by simply joining an N-type and a P-type material together. Nothing more. Just the joining of one material with a majority carrier of electrons to one with a majority carrier of holes. Okay, so the magic word semiconductor is composed of two words, semi and conductor. Semi means not complete, while conductor means something which can conduct electricity. In other words, conductors are a group of material that has electrical conductivity which lies between or exists between metal, or that is conductor, and insulator. And then the conductivity of material can be varied over the order of magnitude by changing temperature and adding impurity. Okay, before we proceed to the operating conditions of a diode, there are two types of semiconductor materials, the element material and the compound material. The element material are those silicon and germanium, and then the compound material is those material that is a combination of two or more elements. For example, the gallium arsenide. So there is a gallium and there is an arsenide. So that's the types of semiconductor materials. Okay, the operating conditions of a diode. There are three operating conditions: the no bias, forward bias, and then the reverse bias. In the no bias condition, if you look at the figure, there is a symbol of a diode with a voltage V sub D equal to 0 volts and the current I sub D equals to 0 milliamp. So no external voltage is applied and no current is flowing. When we say the no bias condition, so the condition will be the voltage in the diode is 0 volts and then the current is 0 ampere. So that's the no bias condition. And if we say forward bias condition, the current still flows from positive to the negative polarity, but the diode is identified what material is used. Okay, so when we look at the ideal diode in the no bias condition, we can see here that it is using an ideal diode because the voltage is 0 and the current is 0. But in the forward bias voltage, in the forward bias condition, the convention of the current flows from positive to negative, and then the diode is identified, and we identify the material that is used in the diode. So in the silicon diode, the voltage is 0.7 volts, and when we use germanium diode, the voltage is 0.3 volts. Okay, and in the reverse bias, the current flows from positive to negative. So reverse direction with the forward bias. But if you look here, the polarity is still positive to negative. Actual diode characteristics. So if you look in the graph, so note the regions for no bias, reverse bias, and forward bias conditions. Look closely at the scale for each of these conditions. So if you look at this graph, you'll see here that the no bias is in the origin, meaning V sub D equals to 0 volts, I sub D, or the current equals to 0 milliamp. And if you look at the forward bias, so it already has a voltage. So there's a voltage already. And then if you look at the reverse bias region, there's also current flowing through it, and then there's voltage in the diode. Okay, what is a Zener diode? A Zener is a diode operated in reverse bias at the peak inverse voltage. So this is the symbol of Zener diode. So the line at the tip of the triangle is not straight, rather it looks like a letter Z, slanted letter Z. So that's a Zener diode. A Zener diode is operated in a reverse bias at the peak inverse voltage called the Zener voltage. So a Zener diode has a Zener voltage, and its voltage is 1.8 volts to 200 volts. So it varies from 1.8 to 200 volts. So this is the region where the Zener voltage is located. So it is below the reverse bias condition or reverse bias voltage. The diode is in the reverse bias condition. At some point, the reverse bias voltage is so large, the diode breaks down. The reverse current increases dramatically. Okay, so the maximum voltage is called avalanche breakdown voltage, and the current is called avalanche current. Okay, so in the Zener region, the maximum voltage is called avalanche breakdown voltage, and the current is avalanche current. That is for the Zener diode. Okay, resistance levels. There are 3 types of resistances. Okay, semiconductors act differently to DC and AC currents. So there are the 3 types are DC or static resistance, AC or dynamic resistance, and then average AC resistance. Okay, in the DC or static resistance, the resistance of a diode at a particular operating point is called the DC or static resistance diode. It can be determined using this equation. R sub D, so D means DC or static resistance. R sub D equals to V sub D divided by I sub D. So if you look at the equation, it's just the Ohm's law equation. So the Ohm's law equals to voltage equals to current times resistance. So it is same here that the resistance equals to resistance of a DC resistance equals to DC voltage divided by DC current. Okay, so the difference between the ideal diode and the silicon diode when we compute the DC or static resistance. So the equation used is the one that is given. R sub D equals to V sub D divided by I sub D. So it's here when the current is 20 milliamp, that is 20 M meaning milli, because it is already written in the upper part that the unit is ampere and the voltage is volts and the resistance is ohms. So when current is 20 milliamp, the voltage in the ideal diode is 0, the resistance is 0. But in the silicon diode, when the current is 20 milliamp, the voltage is 0.8 and the resistance is 40 ohms. And if the current is 20 milliamp, the voltage in the ideal diode is still 0 and the resistance is still 0. But in the silicon diode, when the current is 2 milliamp, the voltage is 0.5 volts and the resistance is 250 ohms. So that is the difference between an ideal diode and a silicon diode. Okay, DC resistance or forward bias region decreases when higher currents and voltage. Okay, so if you look at the table, the higher the current, the higher the voltage, but the lower the resistance. That is in the silicon diode. Okay, so another example, if in the ideal diode, if the current is 0, okay, if the current is 0, the voltage equals to negative 10 volts and the resistance equals to infinity. But in the silicon diode, when the voltage is negative 10 volts, the current is negative 2 microampere, and the resistance is 5 mega ohm. So big letter M, that means mega. 5 mega ohms. Okay, so this is the graph of the table that is presented. So the red line indicates the data of the silicon. Okay, so when the voltage in the silicon diode is 0.8, the current is 20 milliamp. And when the voltage in the silicon diode is -10, the current is -2 microampere. Okay. AC or dynamic resistance. Static resistance is using DC input. If the input is sinusoidal, the scenario will be changed. The varying input will move instantaneous operating point up and down at a region. Thus, the specific changes in current and voltage is obtained. It can be determined using equation R sub D equals to the change of voltage of the diode divided by the change of the current in the diode. Okay, that is for the equation for the dynamic resistance. Okay, so the difference between the equation of DC resistance and the AC resistance. In DC resistance, the symbol on the equation, the symbol of the resistance is big letter R. Okay, let's go back. Let's look at big letter R with the big letter D subscript. And in the AC resistance, the symbol is a small letter R with a subscript of a small letter D. So R sub D equals to the change in the voltage divided by the change of the current in the diode. Okay, so this is the presentation of the changes. So the change of the current and the change of the voltage. Okay, average AC resistance. So the symbol of the average AC resistance is R with the subscript of AB equals to V sub D divided by I sub D. That is point to point. So AC resistance can be determined by picking 2 points on the characteristics curve developed for a particular circuit. So in this figure, there are 2 points that are shown. So from the first point to the second point, the upper part, so that is the change. There is a change in voltage, and in a horizontal line, change in voltage is calculated, and in the vertical line, the change of current. So by getting that, you can use that data to find the average resistance. Example: determine the forward voltage and the forward current for the diode in figure 1.2. So that is the figure below, for each of the diode model. Also, find the voltage across the limiting resistor in each case. Assume R sub D equal to 10 ohms. That is 10 ohms. Assume R sub D equals to 10 ohms and determine value of forward current. Okay, so the figure is given. Okay, so these are the solution. If an ideal diode is used, the voltage is 0 volts, the current is 10 milliamp, and the voltage of the limit resistance is 10 volts. And in practical model, so 0.7 volts, meaning that is a silicon diode. When we use silicon diode, the voltage is 0.7, the current is 9.3 milliamp. In the complete model, forward current is 9.21 milliamp and the voltage is 792 millivolt. Okay, in the complete model, we use the whole figure, no, with the two resistances and a diode with the supply. Okay, diode testing. There are diode checker, ohmmeter, and curve tracer for diode testing. For the diode checker, many digital multitesters, that is DMMs, have a diode checking function. A normal diode will exhibit its forward bias voltage or V sub F. The diode should be tested out of circuit. So that is the diode checker. Ohmmeter. Okay, ohmmeter can also be used to test the diode. A normal diode will have the following readings. And then the diode should be tested out of the circuit also. Okay, so ohmmeter, when checking a diode, if the red lead is connected to the positive side of the diode and the black lead or the common is connected to the negative, the reading should be a relatively low resistance. But when the black lead or the common is connected to the negative side of the diode and the red lead is connected to the positive side of the diode, the reading should be relatively high resistance. So that is the testing of a diode using an ohmmeter. And then you can also test a diode by using a curve tracer. A curve tracer is a specialized type of test equipment. It will display the characteristic curve of the diode in a test circuit. This curve can be compared to the specifications of the diode from a data sheet. Okay, so every diode, or shall I say semiconductor, have a data sheet. So a curve tracer is a very nice tester for a diode because it can generate the voltage and the current of the diode. So that's it for chapter 1, Semiconductor Diodes. If you have any question, you can message me you can message me or put a comment in the comment section. Thanks for listening.